Okay, Natural Resources class. Today I'm going to insert a little piece on soils, a little geology lecture into the agriculture section. The reason being, we were talking about environmental impacts, and I just breezed over any association with fertilizer. And I did that because I want to cover that in just a little bit more detail here and add your second video assignment, an assignment to watch a video and give me a question or comment on it. So anyway, today's lecture will be on soils, and you can see the picture of soils much like you would see probably north of here, Hinckley and north. That's what we're going to start with. So what are soils? Well, a geologist would define soils as the loose material that overlies bedrock and supports plant life. Now, I don't know what it is in science. We always have to have a definition, and then we try to fit everything into that definition. My predecessor here used to talk about 4 words he never wanted to hear people say, and those of you that have had me in geology remember me maybe mentioning this. His name was Russ Johnson, wonderful old gentleman, and strong Swedish brogue, and he would say 4 words, kids are baby goats. He would say bugs are insects, weeds are just plants growing where we don't want them, and soil and dirt, he would say, never say dirt. Dirt is soil, he would say. And so we're talking about soil today. There are really 2 types of soil, and if you look at this picture here, we can see both types represented. A soil is formed bottom up, and if you remember this from forestry, we talked about it when we were talking about types of soil for fire breaks. I mentioned that you want mineral soil and not organic soil. If you remember, it was because organic soil can burn, mineral soil does not. Mineral soil is created as rock weathers, and that's what's going on here. This rock is being broken apart, probably mostly by chemical factors. Not around here, it would be also probably a lot of freezing and thawing action going on. Frost can penetrate 4 feet in the ground. It frequently does around here, and so those forces, chemical and physical, are going to be breaking these rocks apart, weathering them, breaking them into smaller pieces, and creating mineral soil. Up here you see some vegetation, and as that decays, it's going to break down and create organic soil, which you'll see up here. And so right in here is a mixture of both mineral and organic soil. And so really, if we look at the particle sizes there are 3 main particle sizes when it comes to soil that we're going to be talking about: sand, silt, and clay. And if you look at some pictures of those sediment sizes, you can see them here. Now, in your notes, I believe I gave you some measurements, such as clay size particles are less than 1/256th of a millimeter. If you can imagine measuring that, that would be difficult to do. Clay tends to be very platy, very flat or dish-like, and that's what you see stacked together here are lots of clay particles. Back here is a quartz particle. Look how big that is. That would be analogous to a sand particle, if you will. So clay is the smallest, and then we would have silt-sized particles, which you see here. About 1/10 of a millimeter is what you're looking at here, and that's a silt-sized particle. And then the largest size particle would be the sand size particle, and here you can see an artist's representation attempt to represent those different sizes here. This picture that I kind of went past kind of quickly is an electron micrograph of clay, another one of clay, and it's kind of neat to look at. Very a flat dish-like, platy we would call it in geology, types of particles. A geologist gets very excited when talking about particle sizes and will oftentimes bring up the soil triangle here. And any soil can be classified using this triangle. If you notice here, as you go down this axis, the percent silt increases. As you go along this one, the percent sand increases. And up this one, the percent clay increases. So at each corner, we have one of the 3 soil types: clay, silt, and sand. Of course, any soil any soil type is going to do different things or provide different things for plants growing in it. I'm getting a little ahead of myself, but right now, if you look at the triangle, the part that gets soil scientists most excited is right here. That's the sweet spot, the bullseye. A loamy soil is the most fertile soil when it comes to growing plants, pertinent to agriculture, what we're talking about here. So when you look at plants growing, that's what they're needing here. If you look a little more closely at this field, you can see there are areas of this field that contain plants that are growing well and others that are displaying diminished capacity. It's actually a chlorotic look, a bleached out, sort of a yellowing, if you will. And we'll talk about what's going on there in just a minute. So back to this. Clay, silt, and sand are the three soil particle sizes. And if you look then at let me just click this off here. If you look then at I think this is what you folks are looking at, something like this. Okay, so we're right about here. There are three things I mentioned here that soils are going to produce or provide for plant growth, and that is water, air, and nutrients. And of course, they're not going to be providing sunlight, so water, air, and nutrients are the three main things that soils will provide for plant growth. And if you think about the three soil types, sand would do a good job of providing air for plant growth, but not so good at providing water, which would just drain right through sand quickly, or nutrients, because the water draining through the sand would drain the nutrients or wash the nutrients away quickly, and they wouldn't stay in the soil profile. Okay, we talk about a soil profile. That would be this unit of soil above bedrock. That would be we're looking at it in cross section or in profile. So that would be the soil profile. It's thin in some areas and thicker in other areas. I mentioned tropical soils and showed you some pictures of them. Here's a good image of a tropical soil. A very thick profile, but very nutrient poor because of all the water that's washing through that and washing the nutrients away. Okay, so if we go back to, well, here's some other looks at soils. When we say deserts, this is what people commonly think of, but deserts really don't have that many big sand fields like this. Deserts more typically look like this, just gravel and boulders at the surface with a few sprinkled sand fields in them. This is one we already looked at. This would be an alpine soil where there's not much soil, a little bit of gravel. Plants cling to that little bit of soil, and then we go to a tundra region where we have just gravels. I've been to the tundra, and it's kind of interesting. Oftentimes, if you kind of look out over, we were in Nome, Alaska, and there's this little 6-inch, 12-inch tall shrub that grows over most everything, or mixture of shrubs, and it looks very green at sometimes of the year. But if you part those little shrubs apart underneath, this is all you see. It's just gravels, and so those different regions of the world would provide different types of soils for plant growth. Okay, and so obviously we're looking at sand. Doesn't do great at providing anything but air. If you can consider clay, those clay soils, if I go back to this picture, clay is going to do a good job of providing nutrients, or can do a good job of providing nutrients for plant growth. We'll talk about that in just a second here. The nutrients tend to hang on to these clay particles and hopefully are available for plants. Now that's going to be a key point. The nutrients might be in the soil, but they are not always available to the plants. In other words, plant roots can't always pry them away from the soil particle. That's a little bit of a foreshadowing, but just remember that. So clays would do a good job of providing nutrients, or can do a good job of providing nutrients. They can do a decent job of providing water, but sometimes these clay soils pack so tight together, and the water can actually be held so tightly to the clay particle that plants, again, can't pry it free. It's actually got a name. It's called hygroscopic water. It's there, but plants can't get it. Generally speaking, though, clay does a good job of providing nutrients. can sometimes do a good job of providing water, but doesn't do a good job of providing air for plant growth. Those soil particles pack too tight together, and there's not that much air there, not enough for plants to do well. Silt is the magic area. We looked at a loam, silty loam. That's the kind of soil that does the best job for plant growth. It provides all three: soil, nutrients, water, and air for plant growth. So, if we're thinking about then that topic of soil fertility, go back to your notes here. Show you where I'm at. I tend to wander around a little bit. Okay, so right here, we were talking about that. The three different types of soil particles and what they provide for plant growth. Another thing that soil contains that's important for understanding how plants grow is humus. If we look at this picture of an area by Cannon Falls, this is a standard Minnesota soil. And Minnesota has, well, the southern and some of the western portions of Minnesota have really fantastic soils. And if you look at this agricultural field, it's just dark, rich soil. That's because it has a lot of humus. In the background, you can see a cornfield that's probably being harvested, and this farmer is going to do very well. Okay, now this is interesting. Notice how they turn the field over. This field has been worked or cultivated, turned over, I should say, and this is October 23rd. And the problem with that can be that that soil then will have snow sitting on it. The snow will melt and run off, and that can carry nutrients and soil particles into nearby streams. So farmers don't know this, and they want to minimize that. So what do? Well, some farmers are going to no-till, and that means they don't till it up. They leave the stubble on the field. Sometimes you can't do that in Minnesota, though. The springs are too wet, so farmers have to do it in the fall when they can. And they try to minimize the effect by putting shelter strips here along the edge of a field so that anything washing off it is captured there. But that's just a good example anyway of humus. So when we talk about humus, what is humus? Well, humus is partially decayed plant material. And if we look at the life cycle of plant residues, this picture can hopefully tell us something. So over here in this box, we have plants represented by this box. The plants die at some point and become residues. Those plant residues have two pathways they can take. The resistant parts of those plant residues will decay slowly and become humus. Now, humus is partially decayed. That means that this decay process has been stopped or slowed down dramatically. The simple components can also end up there. They can also end up as mineralization. That means they become mineral soil, and they're a different product then. That's the soil that won't burn. Even plant material can eventually form into that. It doesn't just form from broken down rocks. So here, the end result here, though, is this humus. And so the goal of farmers is to keep as much humus in the soil as they can. And so if you look at humus contents in various parts of the country, in Utah, look at this. This is organic matter, or humus right here, and this is percent. And you can see any little organic matter or humus that they have goes away very quickly. So this is increasing soil depth as you go down here, and this is increasing organic matter, increasing humus as you go across the top. They have very little in Utah, and it's not very deep. In Minnesota, look at this. We're way over 8%, and it stays deeper in the soil. And then in Indiana, they've got a lot, but it goes away quickly. And the reason for this has a lot to do with precipitation. If you look at this map, there's a line here, 25 inches less here or more here, and Minnesota's right in this band. See, if you have less precipitation, you don't have as much natural plant growth because there's not as much precipitation, so you don't have as much humus building up in the soils. If you go here, east of Minnesota, there's more than 25 or 30 inches of rain a year, and that organic matter can get washed out. That is reflected in soils maps. This green, I wanted to go a little bigger here. This green area here is called mollisols. This is the breadbasket soils, if you will. And these alpha soils aren't bad either. Okay, that's where you get really your best soils. Another map which I'm going to refer to and is a little more complicated is this one here, and this is a soil productivity map. And so you see the most productive soils in our country are through this midsection of our country, and it has to do with rainfall, it has to do with humus production, and it has to do with where we have our farms. Okay, so if we go back to that picture and you look at your notes, right here we've talked about humus and how it's made, and I want to underscore this concept that humus production is good for any kind of soil. If you have a sandy soil, it will make the sand better at providing nutrients and water. It will pry apart the clay particles, hold them apart a little bit so that they're better at providing water and air. And it will just make silt soils just better all the way around. So humus definitely improves all types of soils. There's another aspect to soil fertility that I want to talk about. It's cation exchange capacity, or clay content. If you'll notice in your notes, cation. A cation is a positively charged atom or molecule. Okay, exchange means it's able to provide that to plants. That's what the exchange means. And the capacity, how much is it able to do that? So a soil's ability to provide these cations, these types of molecules, for plant growth. And really there's three kinds of particles that we're interested in. If you look at a fertilizer container, pretty much most fertilizer containers will have these numbers on them somewhere. Most of them have them right up front, 15, 30, 15. Those numbers are there to represent the percentage of cations, of essential nutrients that are in the fertilizer and available to the plants. The first one is always nitrogen. The second one, 30 in this case, is always potassium. Phosphorus, I'm sorry. Nitrogen, phosphorus, potassium. NPK. Okay? That's the order that they occur in. That's the order they are represented in a packaging like this. Nitrogen, the first one. If you want more stem growth, generally speaking, you want more nitrogen. If you want a fertilizer that's going to provide you big blooms, big flowers, lots of fruits, if you will, you want lots of phosphorus. And potassium is there just all around. It's essential for plant growth. Now, all of these are essential. There are others as well that are needed for plant growth, but these are the big three. NPK. Nitrogen, phosphorus, potassium. Now, when you buy something that's organic in the store, one of the reasons it's called organic is because the fertilizer that was used to grow it is organic. And organic simply means it came out of the south end of a north-facing cow or sheep or pig or whatever. So inorganic, when I say inorganic fertilizers, I'm guessing a lot of times that conjures up images like this. Oh, chemist ghoulishly conjuring up some cynical, diabolical substance in the lab, and is going to expose you to it. Well, in reality, these three nutrients have a different source. Okay, now definitely they are processed in industrial processes, but generally potassium comes from rock that's mined in an operation like this, sometimes underground like this, and it's extracted from that rock, not a diabolical chemical process. Phosphorus, basically, if you find anywhere that has phosphorus-bearing rock, apatite, or a lot of bones. They used to make phosphorus fertilizer by treating bones with sulfuric acid. Most of bones have calcium and phosphate in them. If you take acid, you dissolve away the calcium, you leave the phosphate, there's your fertilizer source. Well, they found rock with it in too, and they treat that with acid. It frees the phosphorus, and away you go. And then and there's a phosphate mining operation. And then nitrogen mainly comes from the ground also. It's usually obtained from natural gas. So those three generally occur as cations. Nitrogen, oftentimes used in the form of NH4 plus ammonium. Phosphate occurs P2O5 plus. It's orthophosphate is a generic name for that. And potassium is a positively charged atom on its own. So they're all positively charged. They're all cations. And so this whole term of cation exchange capacity, that's what's going on. And so the ability to provide those for soils is important, and the source of inorganic fertilizers maybe isn't quite as diabolical as we might think. They come from the ground too. Okay, there's now you have a background of the sources and needs of fertilizers for plant growth. I'm going to have you watch a video clip, The Minnesota Millennial Farmer. I will post that link on Moodle, and I would like you to, again, email me a question or comment you have after looking at that video to get credit for having looked at that video. And I'm anxious to see your responses to it. The video deals with application of fertilizer. You get to see some of the mechanization, how it's actually done. You get to see an introduction to precision agriculture, how precisely they can apply that. He also talks about their desire to not put more on the field than the field needs, because that's a waste of money, and also gives you another look at precision agriculture at the end of the video, the use of GPS in controlling that heavy equipment very, very precisely. And yeah, and look for that link. Thank you very much, and have a good day.